I'm going to show you how a small team of just 4 engineers managed to disrupt the company they were working for by rewriting from scratch their entire system while maintaining the current one in less than a year. The startup world is really tough. You are in a fast-paced environment where there is a lot of learning and moving parts, and all that requires a lot of effort. You need to work hard to keep your clients happy while trying to get new ones, with a lot of competition. So how do you manage to get on top of all that? You try different solutions to solve your most immediate problems, and you keep around those that won't imply a lot of effort to maintain or set up, and keep improving them, make them faster, secure, and easy to use. So I'm going to walk you through our use case, how we moved from a monolithic app into a distributed system, what were the problems and the needs that we have, and how we solve them. And I'm hoping somehow you will feel identified with our use case. I'm going to start with a brief introduction of what we do at Moltin, the company I work for, then to deep dive into how it looks like before adopting microservices and after adopting microservices. When did we feel the need of having a service mesh, and why? And what we're planning on doing next. So Moltin, it's an API first that offer a commerce experience. So you can build your online shops using a friendly API. Products, brands, categories, payment gateway, all the things that you can find on e-commerce. We are a small startup that is growing now, and we are about 20 employees. So let's go back in time. It's 2015, end of 2015, beginning of 2016. We are 4 engineers, and we are in front of a huge monolithic app building PHP 5 and Laravel 4 that has been around for a while. The code is highly coupled. There is no test at all, poor performance, and high latency responses, which we can translate that in a not really ideal situation, neither for us, the developers, and our customers, the users, that and more at that point that we were having more and more people using us, and the performance of the system was even worse. So how do we look like at that point? We had an unhappy user there using our monolithic app, and the code is really coupled, and that's why I try to represent with those circles. So one of the first tasks that we had to do was increase the performance of the application, and therefore they decrease the response latency, something noisy in a system like that one. So how do we solve it? We try to identify the most used part of the system, and from those, the slowest one, and we improve it. So what would you say is the most used part in a SaaS platform? And this is kind of rhetorical because I'm going to ask for it. And in our case, will be the most used and the most slowly performing part. It's a authentication system. You need to validate every request that comes into your system. You need to check that that guy that is doing the request have a valid store that haven't reached the request limit and is using the right scope to the resource that he's requesting. At that moment, we have 500 milliseconds to get an access token, completely unacceptable for an API, and more or less around the same time to validate the access token, a little bit less. So how do we approach a solution here? We tweak the code a little bit. We refactor some bits, but as you can imagine, that was pretty complicated. We improved the database communication because there was a lot of requests doing the same, and we cached some of those, and that helped a little bit. And we add indices over some tables. And we managed to get down those 500 milliseconds to 250 milliseconds. We were really happy at that point because we finished our first task, and we couldn't halve those 500 milliseconds. But obviously, that's not enough. So at that moment, we face a barrier. We have to choose in between keep trying to improve the PHP code, the legacy code, and make it faster, thing that we wasn't sure that we will be able to do, or decouple the code and pull out the authentication logic into something else. We did that, and we used Lua scripts and OpenResty, and that's where we thought our first microservice is born. And we managed to, with the right technology for the right job, reach the maximum performance, and we managed to get down those 250 milliseconds to 40 milliseconds, which is way better. That's to get an access token. For validate is less. So how do we look like at this point? We have a happy customer now, a little bit more happy because there's still the monolithic there. We have the authentication layer using OpenResty and Lua scripts, and that's using Redis as a cache for the access token, and that's redirecting the request to the monolithic app. So why microservices? We needed to improve drastically the performance of our system and reduce the request latencies. And we used proofs ourselves that with the authentication approach of choosing the right tool for the right job was the way to go. So, but how? How do you transform that monolithic app into a distributed system? Well, can you read that? No. That's 2 weeks ago, our friend Martin just tweeted this, which is it's a blog post where he's explaining exactly step by step how to break the monolithic into microservices. And even better, he's using an e-commerce example. So that would have been great 2 years ago for us, but we didn't have it. So how did we approach it? So we sit down as a team and we take a decision that will be crucial for the company. So we have to decide if we keep pulling bits of our monolithic app into microservices, or we rewrite from scratch the API. We knew that that would be fun, but really tough to maintain the old system while building a new one, while learning a lot of things in a very small team of 4 engineers. Crazy. So, as you already know, we took the radical approach, and we rewrite all the things. But I have to say that I wouldn't recommend it. It will depend on your use case. It did work for us, and this is one of the reasons I'm here today. The company is still working. And I found a couple of weeks back, the same time that I found Martin's tweet, the next slide, which is a tweet that is perfect for that slide, and it was an inspiration for last-minute change on this presentation. Sandeep Dinesh, developer advocate on Google, he said, a good company team will try to disrupt themselves by building the replacement while trying to maintain the current system, which is easier said than done. And that was just perfect for us. Like, we were really happy about reading that tweet. So how do we look like at that point? We have, right now, around 17 microservices in total. We use 5 different language programs, JavaScript, PHP, Go, Lua, and I don't remember the other one, and 5 different databases, Scala, Mongo, Elasticsearch, Redis, and one queue system, RevamQ. And we are using the same authentication microservices that we pulled out from the monolithic app 2 years after. So we already have our distribution system working, and I haven't explained how and where we are using the service mesh. So let's explain what's service mesh first. It's a dedicated infrastructure layer for service-to-service communication. The most important part is that it's decoupled from your application code, and it's focused on services and requests. So why do we need a service mesh in the first place? Well, communication between services needs to be managed, monitored, and controlled. But we have an immediate necessity when we were building our system, which was observability. That was one of the main reasons we started using the service mesh, but probably because we didn't know enough at that time about all the resilience speed that you can get out of the service mesh. So we needed to be able to debug internal communication to know what was going on. We didn't want to bake that inside of our applications. So for development, if something is broken, where do you even start looking at? So did my request go from A to B? Where is it hanging? Why my system is so slow? So developing the microservices independently was amazing. There was a learning curve there to learn the new language and how to interact with the database. But the tricky bit came later when you try to put them together. In production, you want to have a resilient system. You want to have a high rate of high success rate, reduce the tail latencies, and obviously metric and tracing. So I'm going to go through two scenarios, circuit breaking and load balancing. So that will be a circuit breaking problem, which is you got a happy user using our system. We are using the API gateway pattern to compound the responses from the different services. And in this case, he's doing a request to products. So his request goes through authentication. We validate the token, go to gateway, gateway gather the product, gather the settings, build the object together, and then it's going down to currencies. In this case, we have two currencies, and there is no service mesh here. So that service there have a 70% error rate, which means it will fail 70% of the time, obviously. But it's low balancing between those two. So if we had a service mesh here, that wouldn't fail because service mesh will be smart enough to be able to know that that container there, it's failing 70% of the time, and instead of redirecting the request from gateway to that container, we'll be using the healthy one. And the request to the user will be successful. And more or less the same happened with the latency-aware system. So in this case, instead of an error, the service mesh is smart enough to know the settings taking longer than normal, and it will stop using it to use the container that is healthy than that one. And when it does that, it will allow that container, maybe, to get healthy. Like, it will stop, finish doing whatever it's doing and consuming, I don't know, if it's consuming CPU or RAM, it will release that from the node and maybe go back. The service mesh will be checking that. So what's out there? We have different service mesh solutions. Linkerd can do it, which is like Linkerd from Linkerd guys for Kubernetes, but way faster because it's built on Rust and Go. And Envoy and Istio, that they play together very well. Why Linkerd? Why we use Linkerd? Why we choose it? Because it was vendor agnostic, and at that point we didn't know which orchestration layer we were going to use. We are using Rancher right now, the older version, which is using Cattle. We're not using Kubernetes. But thanks that it's vendor agnostic, we can move to Kubernetes without doing pretty much any change with the configuration that we have right now with Linkerd. At that moment, it was a stronger option. It was well adopted by the community and trusted by multiple companies in production. And it has a great support. So what is it really, Linkerd? It's just another proxy with a different feature set. With a feature set that is different. So for example, if you have two services communicating and it's A to B, you put Linkerd in the middle to manage those communication between those two services. So you might be asking yourself, by adding Linkerd, will that affect the performance of my system? Yes, it will. In your best case scenario, you will have a small performance implication, negative. But it's your worst case scenario, the one you worry about, and that's where you will be gaining a huge performance improvement. So our goal in a distributed system, it's you want to reduce the tail latencies, the P99, and you want to have a stable and resilient system. And that's where the service mesh plays well. So what else we can do with Linkerd? We can do load balancing, logging, error tracing, tracing metrics, retry budgets, timeouts, a lot of things. How much of this are we using today? Not even the 50% of all those features. But that's fine. That's all we need. It helped us to build this new system with confidence in such short period of time. So when we first started using it, we got it working in less than a day. And pretty much out of the box with minimal configuration. And we are still using most of the default values. So we have tweaked like the response classifier to retry 500 on independence request, for example. But if you need, you can go and tweak it granularly. So how do we look like? That's our system right now. We have a load balancer here. The request comes into the router on Linkerd. That's sending the request down to authentication, which have Redis as a cache layer. And then it goes down to another. It's the same Linkerd, but those are different routes. So we can have different configuration for each tier in the system. And we are using Linkerd with Namerd, which is basically another service that you can attach to Linkerd, and you have an API to dynamically change the routing on Namerd. And those all are the databases that we're using. So what's next? What we're planning on doing next? We want to do more cool things. we got a very peculiar setup right now. So we don't use staging. We don't have a staging environment. We use production environment, and we deploy directly to production. But we need to improve the workflow a little bit. We want to do Canary deployments, sharding traffic, and dark launches. Those are things that you can manage to do with named and Linkerd, obviously. So that will be the Canary example. You got you service running there in production, and that's the new version. And you deploy that, but you don't release it, which is, there's a big difference between releasing and deploying. So you deploy that, you don't release it because no one is going to get access yet to that. And then you start redirecting traffic to it. So thanks to named, from the CI, you can change the routing table dynamically and reroute the 10% of the traffic to that new version of your system. So you monitor there if your system is working properly, if you don't have any alerts, and if it's healthy to keep going and redirect more traffic, 50%, 70%, 100%. And then you're happy you replace your old version of the container with a new version. You can do something like sharding traffic as well. These all are like techniques to test in production. You got the user which is doing a request, and Linkerd is able to like mirror that request to two different containers, two different versions of your service. But one of them is not replying. Okay, just that one, which is the stable one. That one is the new one, for example. But you get some real traffic into that service, and that will allow you to know if an error is happening. You see you're tracing, you're logging, and you will be able to know if that new version is functioning, is working properly. Another cool thing that you can do is dark launches. You deploy a new version, different one from the other one, and you only let several, your QA engineers access to that new feature, so they can test that feature. And you can do that by a header on Linkerd, and redirect per request. It will be redirected to that one. So it's a way to testing on production, because obviously in production, production and staging, you need. It's really difficult to keep staying in sync with production. So we want to introduce all these phases to be able to have a more tested product. So we're looking forward here to move to Kubernetes, but probably using Linkerd as we have it right now, with a small configuration changes to use probably the Kubernetes resolver. And eval can do it, obviously. We want to check and do it and see how it works with Kubernetes. Few takeaways. Network communication is complicated. Apps shouldn't have to reinvent the wheel. And libraries are language specific. So you will need a service mesh if you are building a distributed system. I don't know how much time do I have. That was too fast, I think. I think we can do a demo if you want. I can show you. Where hell? What is this? Reference. So I'm going to show you an example. Can you see that properly? So I'm going to show you an example, which is add a step example. And here you can see how, let me see if I can show you, because the quality is horrible. In here, we can see how, I'm gonna run this example, which is basically, we have a slow cooker, which is a benchmarking, and it's gonna be using Linkerd in the middle to redirect traffic. This will be like a user, the benchmarking, and that will be accessing to our microservices on the top with Linkerd. And the one in the bottom is without Linkerd, and we'll be running those services that have like a really high latency, and several amount of requests will fail. And we can see here how the one that have Linkerd will be even faster than the one without Linkerd. So introducing Linkerd will help you in your worst case scenario to have a better performing system. So if we go back, you can see here the decompose file. And you can see how it's going to be creating all these containers that, where are they? OK, yeah, we are passing here the latency. So each one of those have a different latency, but they are the same, like the baseline and the Linkerd one. It's like a mirror, but without Linkerd in between. And that's the success rate there of 60%. So if decompose up. That's running all the containers and the benchmarking, Grafana, Prometheus, that is gathering the metrics from Linkerd, and Grafana is going to create a graph for everything. We can do here. Open. South, I think. That's very small. I don't know what's going on here with screen. Scale, Vista. Yes, OK. So, well, I just basically start running it. So you will see how it will take a while to link it to be smart enough to know how the system is performing and to really make the most of knowing how your system is behaving. You know, you will be able to see how Linkerd will be able to know which containers are working in an unhealthy way or are less faster than others. So we can see here the throughput on the top. Linkerd is already processing 230 requests per second. I think we're sending 500 requests per second to each through the benchmarking. But the baseline is just processing 90% of the requests. So it's not able to do more requests because it's hitting all the containers at the same time. While Linkerd is smart enough to say, well, that's a slow one. I'm going to, instead of redirect the request to that one, I'm going to be using that one. So that would be your best case. You can see here how Linkerd, well, no, that's the, yeah, not that one, yeah. A slow cooker, sorry, the Linkerd is using 47 milliseconds, while baseline is taking 172 milliseconds, average, 80, 30 something. So there is not much different here. There is different, but not much. And in here, which is the normal case, you can see the different metrics there. The baseline is taking a lot. It's like taking 1 second and something, and the other one is taking 800 and something. And the worst case scenario, you can see here how that bit there, that's the time that takes Linkerd to know and to understand how the containers are behaving, to stop sending requests to those. And I think I can show you the Linkerd example. So basically, it's using the E1 load balancer, and it's checking for 90% of success rate on 20 requests. So it will be doing 20 requests per service. And if that service has a success rate of 90%, it will keep it on the pool, and it will use it again. If that's not the case, it will take it out from the pool for 10 seconds. And then we'll back off for 10 seconds, and we'll retry again. That's why we can see here that at the beginning, it takes a while to understand how the services are behaving. And I think that's everything that I have to. Nope. Oh man, how do I? Yeah, okay. So that's. I'm Israel Sotomayor. I'm an infrastructure engineer at Moltin. I'm a digital nomad. That's my house right now. And I'm enjoying automated things and love traveling, of course. Thank you so much. Questions? I think you have to use the micro in the middle, sorry. See anything? You finished too early, yeah?
You were talking about the performance hits.
Yeah.
And what if all the apps that you had in the example, if they were behaving correctly, what would be the performance difference then?
If they will be behaving correctly, they will be baseline will be behaving a little bit better than Linkerd, because you are with Linkerd you have that your best case you have that performance implication, which is around 1 millisecond, 2 milliseconds less. Yeah, it's not that much. On Conduit, which is built on Rust, is way faster, and that's just basically nothing. So.
In the presentation, you said that you chose Linkerd because it was the best at the time for you and for your use case. And what do you think is the best now? Or what would you choose if you would like to start with Service Mesh to get easy into it and try those features and getting these things?
Probably we won't be using Rancher, we'll be using Kubernetes, and we will be choosing Conduit, because I do love Rust and the performance you can get out of Rust. And we haven't tested yet, but I'm pretty sure the performance-wise is going to be amazing if you change it. And the footprint on the service is going to be way smaller than Linkerd. The memory usage and CPU usage.
Oh, thank you very much.
Yeah, you're welcome.
Hi. Now that you have microservices and a service mesh, have you thought about breaking down your API gateway into smaller components?
We have, yes. Actually, I don't know if you notice this, I use parentheses to use the microservices word, because not all of the services are micro. They have different responsibilities. And it's sometimes like we have like a currency and settings, which are like 2 microservices that are being hit like per every request. So we were like thinking maybe incorporating those to, a call inside of every microservice to that table as well to get the currencies. And probably removing the gateway and just keep the communication between them. Yeah. Thank you.
Is it doing any proactive, you said about the Linkerd that it's doing any proactive actions when it finds that there are some problems within any microservices?
Sorry, say again? I couldn't hear you again.
I said that you said that the Linkerd can detect that there are some issues or performance between network issues between 2 microservices. Yeah. What happens if it detects it? Is it doing any proactive actions in that case?
Yeah, for example, in the example that I show, it knows it's like it has like a pool of the latencies, for example, in the latency aware example, and it knows that the container is being slower than before and slower than his peers, and it stops sending traffic to that one and it starts sending traffic to the faster one. It depends on how you configure, you do the setup as well.
So it is doing the proxy as well in that case?
Yeah.
Okay, thanks.
Yeah. Thank you.